Okay, are you ready? This will conclude all the theory of limits for algebraic functions. Polynomials we did, and that was easy. All we needed was the repeated application of addition rule and multiplication rule, more precisely speaking, mathematical induction. For rational function, a little bit more confusing, but basically this was polynomial over polynomial after simplification. So we just use quotient rule and then polynomial over polynomial, which we already established here, and that was it. If we complete the radical function, then all algebraic functions will be done, but this is going to be hard. As a matter of fact, this theorem is done by two parts. One is a special case when c is equal to 0, much easier than the other case, so I'm going to leave that to students. And then when c is greater than 0, well, that's not going to be easy, and we'll establish that. Here's a strategy. We're going to find a certain function g of x which is greater than or equal to the absolute value of nth root of x minus nth root of c. Also, g of x is going to 0. Consequently, this nth root of x minus nth root of c will be squeezed between g of x and negative g of x. Basically, this is what I'm talking about. We're going to be in this kind of situation, and then both g of x and negative g of x will go down to 0 because negative 0 is 0, and consequently by the sandwich rule this middle function will be squeezed by these two upper and lower bounds tending to the same limit, so this will go down to 0. Consequently, this will approach there because the difference became 0. That's how we're going to prove. Now, what kind of g we're going to get? Well, that's the tricky part, and here it is. When x is greater than c, we're going to get the top expression x minus c over this denominator, and this denominator looks complicated, but that's constant. C is constant, n is given. Those are constants, so x minus c and x minus c goes down to 0. How about the next expression here? C minus x, yes, x is less than c, so we need c minus x to be positive. And if you look at the denominator, it's a little bit harder. N times minimum of 1 or x, the smaller of 1 or x. When x is big, then we're going to select 1, so no big deal there. But when x is really small, then you have to select x. But that's okay because x is going to get very, very close to c, and consequently this limit will approach to c minus c over n times c, and that's going to go to 0. So the key point is to prove this inequality for x equal to c, this case. X equal to, x equal to c, this case, and x is less than c, that case. Okay. All right, and let's establish that for x greater than c, when x is greater than c. Here we begin. Let's begin with y equals to nth root of x and d equals to nth root of c. All right, and consequently x is y to the nth power and c is d to the nth power. Nothing fancy, just rewriting the algebraic expressions. And we assumed x is greater than c, right? Okay, so we subtract c from x minus c, which is equivalent to y to the nth power minus d to the nth power. And then we factor it. If we do, we're gonna get this y minus d times this expression. Consequently, this y minus d can be rewritten as x minus c, the left-hand side, over this big expression down there. And let's underestimate the denominator. Y is greater than d, right? Because x is greater than c. Yes, y is greater than d. So if I replace all the y's by d's, then I'm gonna reduce the denominator, which means the overall expression will become bigger. And if I replace all the y's by d's, then you're gonna get d to the n minus first power, another d to the n minus first power, and so on and so forth. They're all d to the n minus first power. So n times d to the n minus first power is what I'm gonna get. And d, by the way, is nth root of c, so that to the n minus first power is this expression, c to the n minus first over n minus 1 over nth power. But it's complicated, but the key point is it doesn't matter. It's just constant. Constant times x minus c, and that did it. We were able to bound this function nth root of x minus nth root of c by some constant times x minus c, which goes down to 0. Okay, one down, one more to go. So that part is done. The key idea was this factorization and this underestimation of denominator. Okay, let's consider the other case when x is less than c. This is harder. We begin with the same thing. Y is nth root of x and d is nth root of c, so that x is y to the nth power, c is d to the nth power. And in this case, y is less than d. Okay, we do the same thing, c minus x, and consequently d to the nth power minus y to the nth power. So if you factor, we have d minus y times this big expression. And in order to overestimate this right-hand side to get something bigger, we have to underestimate the denominator. And underestimating the denominator is trickier this time, because in order to underestimate, we have to get something smaller, and y is smaller than d. So replacing all the d by y, we get this expression, and we get y to the n minus first power. And what do we get? Y to the n minus first power is y to the nth power divided by n. So far so good. And y to the nth power is x. And consequently, we get the final expression like this: c minus x over n times x over y. We are in a bit of a trouble here. C minus x, that's good. And how about the denominator? How about the denominator? Denominator is not constant, so we need a bit more work. Okay, let's consider something further. If x is greater than 1, then y is greater than 1 too. So y to the n minus first power is greater than 1 to the n minus first power, so greater than 1. So we can replace this y to the n minus first power by 1 by underestimating, and we get c minus x over n, and that's good. Denominator is now constant. So we have a function that is overestimating this nth root of c minus nth root of x, but it is constant times c minus x, which is going down to 0 as x approaches c. When x is less than 1, oh, that's going to be more troublesome. So y is less than 1. In that case, we do this kind of manipulation. Y to the n minus first power, y is less than 1, so y to the nth power, which is y times y to the n minus first power, and this y is less than 1, so multiplying by less than 1, we are reducing from y to the n minus first power. So this is what we get. Y to the nth power is less than y to the n minus first power. Y to the n power, by the way, is x, so x is less than y to the n minus first power. So we can replace y to the n minus first power by x, and consequently underestimating the denominator, so the overall quantity was overestimated. So we have this form, c minus x over nx. Putting this one and that one together, we get this expression, n times the smaller of 1 and x. When x is, let's see, when c is sufficiently large, much greater than 1, then when x gets pretty close to c, then x will be also greater than 1, so the denominator will be just n times 1, so we have constant. When c is less than 1, in the worst case pretty close to 0, then the denominator will be just x. But that's okay, because x will get very, very close to c. And what do we get? We get c minus x over c. That's going to go down to 0, right? Yes, x will not go pretty close to 0 or behave really badly. It'll stay close to c, which is constant. So as x gets really, really close to c, we only have c minus x. So in the end, the limit goes down to 0. So what's the consequence? Well, kind of like this. Nth root of x minus nth root of c is captured between negative g of x and positive g of x, and g of x go to 0 as x approaches c, whether it's this one or that one. Consequently, what do we have? Limit of nth root of x minus nth root of c is equal to 0, so flipping one to the other, limit of nth root of x is equal to nth root of c. We get that. Okay, it was very difficult to prove, but in the end we got what we wanted. We're done with all the algebraic settings. After this, we can just plug in numbers whenever we can avoid denominator 0 situation or log of 0 situation, and so on and so forth. Oh, logarithm. I didn't really establish the logarithm yet. Looks like that's something we'll have to postpone. As a matter of fact, exponential and log are a little bit tricky, to tell the truth, because the forward definition we considered in week 1 is not really complete. Exponential of rational power is okay, but exponential of irrational power is not well defined through repeated multiplication or anything like this. So we have to consider exponential and logarithm completely separately using different type of argument. And that's something we're going to do, I don't know, several weeks later, I think, when we have considered integration and stuff. So let's postpone that one, exponential and log. Let's talk about trigonometric functions, these two. Okay, here's a proof of limit as theta going down to 0, sine of theta over theta is equal to 1. We use some geometrical argument, and here is a nice picture that explains everything. Look at the area of this blue sector, and that area of the blue sector is certainly less than the area of this large triangle OAD because the sector is included in there, and greater than the small triangle OAB because the smaller triangle is included in the sector. So we have this relation here. Now area of the smaller triangle OAB is 1/2 1 times 1 times sine of theta from the area formula of a triangle with the angle theta. And area formula for the sector 1/2 times radius squared, 1 squared times theta. And finally, the bigger triangle, 1/2 base length 1 times height. Height is tangent of theta. So we have this relation. By the way, if you're interested in the derivation, here is further relation. You can find out, you can deduce the area formula using the height BE, using OB sine of theta. But if you know area formula of SAS, then you can go directly with this one. Okay, anyway, we start from here, and then we take reciprocal. Divide everything by 1/2 sine of theta. Then we have this. 1/2 is all gone, and the sine of theta was all divided. And tangent of theta divided by sine of theta is, of course, 1 of cosine. Tangent is sine of cosine, and after simplification. Now, flipping everything, we get this. Cosine of theta is less than sine of theta over theta, and in turn, that is less than 1. From here, we can take the sandwich rule. Right hand side is constantly 1, and left hand side, we take the limit as theta going down to 0 from the positive side, and what do we get? This limit is 1 because cosine of 0 is 1. So by the sandwich rule, the middle part, this middle limit is also 1. Oh, by the way, we have to go from theta, we have to move theta is going to 0 in positive side because in order to do all this, the angle theta has to be positive. You see, angle theta is positive, so if I divide everything by sine of theta, I divided everything by positive numbers, so we have no change of this inequalities. And then when we took this reciprocal of everything, again we have all these because everything was positive. Now, what if we have to consider theta going down to negative? We'll have to draw a similar picture, but going down to fourth quadrant. The detail is left to the students. In the end, we're going to get the same thing. How about the proof of the second one? Well, using the first and the Pythagorean identity, we can prove algebraically like this. The detail is left to the students. Compared with the first one with this picture and triangle, pictures of triangle and sandwich rule, this is much easier. Left to the students. Okay, that's it.